What if I told you there's an aircraft so stealthy that enemy radar basically thinks it's a marble flying through the sky? No joke. Tonight we're breaking down the real science and technology behind stealth bombers, the sensors hunting them, and the insane engineering tricks that make a 150-ton aircraft almost invisible. And trust me, by the end of this video you'll understand how modern stealth technology literally hacks physics and radar systems. Alright folks, let's talk about one of the coolest engineering achievements in modern aviation. The Northrop Grumman B-2 Spirit stealth bomber. At first glance, it looks like a giant flying Dorito. But this weird shape isn't just for style. It's the result of decades of aerospace engineering, radar physics, and materials science designed to do one thing: make a massive aircraft disappear from radar. And honestly, the technology behind it is wild. Before we talk stealth, we gotta understand radar. Radar systems work pretty simply. They send out radio waves, which bounce off objects and return to the radar antenna. The system then calculates three things: distance, direction, and speed. Think of it like shouting in a canyon and listening for the echo. The bigger and flatter the object, the stronger the radar echo. That echo is called the radar cross-section, or RCS. For example, a fighter jet might look like a small car on radar. A large bomber might look like a bus. But here's the crazy part. A Northrop Grumman B-2 Spirit is physically enormous. Yet on radar it can appear no bigger than a marble. So how do engineers pull that off? The first trick is geometry. Traditional aircraft have lots of surfaces that reflect radar waves directly back to the radar station. But stealth aircraft are designed with angled surfaces that scatter radar waves away. Imagine shining a flashlight at a mirror. The light reflects straight back. Now shine it at a tilted piece of glass. The light bounces off in another direction. Stealth aircraft use this exact principle. The flying wing design of the Northrop Grumman B-2 Spirit eliminates vertical tails and sharp angles that reflect radar. Instead, radar waves scatter away like light hitting a disco ball. Result? The radar never gets the signal back. But shape alone isn't enough. So engineers added another trick: radar-absorbing materials, often called RAM. These special coatings are packed with microscopic materials that convert radar energy into heat instead of reflections. Basically, instead of bouncing radar back, the aircraft soaks it up like a sponge. This technology comes from advanced materials science involving carbon composites, ferrites, and special polymers. And maintaining those coatings is insanely expensive. In fact, stealth bombers often require hours of maintenance for every hour of flight. Yeah, stealth ain't cheap. But radar isn't the only way to detect aircraft. Modern fighter jets use something called infrared search and track systems. These sensors look for heat, and that's a huge problem, because jet engines are basically giant heat machines. Even stealth aircraft generate massive thermal signatures. That's why stealth bombers hide their engines deep inside the airframe and use specially designed exhaust systems to cool the airflow. But if an aircraft gets close enough, infrared sensors can still detect it. That's where another piece of advanced technology comes in. Stealth bombers rarely fly alone. They're usually escorted by stealth fighters like the Lockheed Martin F-22 Raptor or the Lockheed Martin F-35 Lightning II. These aircraft combine stealth design with extremely advanced sensors. For example, the F-22's PG-77 radar can detect enemy aircraft from over 100 kilometers away. But here's the crazy part. Stealth fighters often detect enemies long before the enemy radar detects them. In modern aerial warfare, that advantage is huge, because whoever sees first usually shoots first. Once stealth bombers reach their targets, the real technology show begins. They deploy precision weapons like the GBU-31 JDAM. JDAM stands for Joint Direct Attack Munition. It's basically a guidance kit attached to a standard bomb. Inside the tail kit are GPS receivers, guidance computers, and steering fins. Once released, the bomb uses satellite navigation to guide itself toward a specific set of coordinates. Some of these bombs can hit targets within a few meters of accuracy, which is insane considering they're dropped from tens of thousands of feet in the air. Stealth technology is constantly evolving. Countries around the world are developing next-generation stealth aircraft. For example, the U.S. is building the Northrop Grumman B-21 Raider, the successor to the B-2. The goal? Even better stealth, better sensors, better networking with drones and satellites. But here's the twist. Radar technology is also evolving. New systems use low-frequency radar, AI processing, and multi-static radar networks to detect stealth aircraft. So the stealth versus radar battle is basically an ongoing technology arms race. Every time engineers make aircraft harder to detect, radar scientists try to make detection easier. Now you might be thinking, cool military tech, but why should we care? Because stealth research has pushed advancements in materials science, aerospace engineering, signal processing, and computer modeling. Many technologies developed for stealth eventually influence civil aviation, satellite technology, and even telecommunications. In other words, military innovation often drives broader technological progress. So the next time you see a stealth bomber flying overhead, remember this: you're not just looking at an airplane. You're looking at decades of physics, engineering, materials science, and computing working together to bend the rules of detection. A 150-ton aircraft, designed to look like a marble on radar. Pretty wild, right? If you enjoyed this deep dive into science and military technology, make sure you hit subscribe because we break down the engineering behind the world's most advanced machines. And if you want to see the next video, we're going to explore how hypersonic missiles travel at Mach 5 and why stopping them is almost impossible. Trust me, that technology is even crazier. See you in the next one.